This is a production of Cornell University.
All right. The next thing then is now let's talk about that variable charge, that pH-dependent charge, and that is associated with that hydroxyl group. Okay? It can be both negative and positive. It's a hydroxyl group, and it's a source of that charge on the humic materials, the oxide materials, aliphanes, and some of these phyllosilicates. Okay. So it's variable. Okay? I've shown all of these pictures, okay, but basically it's these hydroxyl groups that are sticking off, okay, wherever they happen to be. Here's the kaolinite, you have hydroxyl groups up on this sheet right here. Here's some oxide, you have hydroxyl groups on both sides. Here's the organic molecule, you have hydroxyl groups all over the place, okay. Here is that edge, okay, so imagine I'm taking a line and I'm just showing the edge right there. I'm cutting it right where that oxygen is. Here's the oxygen, okay. This C represents the rest of that organic molecule. Okay, this aluminum basically represents the rest of this Gibbsite. Okay, I'm drawing a line right where that oxygen is, so that's basically the edge. This side of that line is the soil solution. This side of the line is the structure. Okay, so if I start changing the pH of that soil solution, so I start changing this side of the molecule, okay, this side of the volume, okay, and I start basically increasing the pH. If I start increasing the pH, I'm going to start adding hydroxyl molecules to the soil solution. I have a hydroxyl here, and I have a hydroxyl here. This hydroxyl is going to go in, and if I keep adding these hydroxyl units, what's going to happen is this hydroxyl is going to bind with that proton and make water. And it's going to pull it off and make water, and the result is that my molecule now has a negative charge. It's become more negative by adding hydroxide. Does that make sense? Questions? All right, let's turn the scenario around. Basically the same graphs that you saw before, but in this scenario, rather than adding hydroxide, I'm going to start lowering the pH. I'm going to start adding protons. Okay? Now, this has a negative charge here. The proton is going to react and bind with that negative charge. And as a result, I'm going to end up with a positive charge associated with my structure. Now, I changed the pH, and this will totally change. But at this pH, where I've added the protons, at this pH, this molecule now has a positive charge associated with it. And that positive charge can hold on to negatively charged ions that are in solution here. As this negatively charged ion that's here, when I have high pHs, can hold on to more positively charged ions. So it's variable. It's pH variable. So the charge associated with this colloid has to do with the pH. Go. Okay, so the question was, if we have a colloid or a particle that's basically binding these cations or anions, and the system goes dry, what happens to those ions? Well, as long as they're bound to this colloid, they will stay in solution. But all the they'll stay in the soil volume. But all the ions that were in solution will go with the water. Does that make sense? And so you see this a lot with this sort of you see it a lot everywhere, but this is really a big effect when you start going out west and you start seeing the salt buildups and stuff like that. No, that's the water moving up. Okay, the salts are not actually being held, but the water itself is leaving because of evaporation, and the salts are left behind. But it's a very similar type of go.
Is that a general rule for most soils that it's more negatively charged than the higher pH?
The question was, is it a general rule as the pHs go high, are the charges more positive on the soils? And the general or negative. So increasing negative, I'm going to increase my negative charge. If I increase the hydroxide, pH goes up, I'm going to get and more negative charge. That is a general, and the other way around. Yes, it is a general trend. Okay? But the reality is you have to have the types of materials that are pH variable. Okay? Let's go back to this slide right here. Okay? No, not this slide. Let's go actually to the next slide. All of these molecules, all of these colloids are pH variable. But if they have more or less hydroxide, they're going to be more or less pH variable. So it's really dependent. That charge variability is really dependent upon that hydroxyl being exposed. Okay? You can certainly imagine a phyllosilicate right here. It has a lot of hydroxyls, but if those hydroxyls are actually interior to the structure, they're not exposed to the soil solution. And if they're not exposed to the soil solution, they're not going to be pH dependent because they can't react with the hydroxide or the proton moving into the system. They will only have hydroxyl units exposed at the edge. Okay? And yes, they'll be pH dependent charge right there, but considering the rest of this large structure, I mean, these are really large structures relative to this edge, really small effect. It's not until you get a really large surface area of hydroxyls that is exposed that you're going to start getting really large pH dependent charges. Okay? Does that make sense? Okay, any questions on this? Okay. The take-home point, and your question basically spoke to this, the charge is only associated, this pH-dependent charge is only associated with those hydroxyl groups. And if they're not exposed, you're not going to get that pH-dependent charge. Now, with the phyllosilicates, the reality is, yes, you have some hydroxyls at the edges. But the reality is, with the phyllosilicates, you're only going to get it really on the 1-to-1 phyllosilicates because it's that octahedral sheet. Remember the 1-to-1s? Okay, versus a 2-to-1 versus a 2-to-1-to-1. Here's my tetrahedral sheet, my octahedral sheet underneath it. They're being bound by those oxygens in here. Okay? If I don't have another tetrahedral sheet down here, these oxygens are all going to be exposed. But if I do have a tetrahedral sheet here, these oxygens are no longer exposed, and so they're not subject to pH-dependent charge. I still have some on the edges, but not on the vast majority of the surface area. Go.
So do the tetrahedral sheets not have the oxygen?
They do, but because of the way they're bound together, that oxygen is not it's not reactive to the pH changes. Cool? Good so far? Okay. Now the cool thing here is, if you think about this, depending upon the structural arrangement, we're looking at all these different colloids, but depending upon that structural arrangement, these colloids, some of them are going to be predominantly permanent charge, some of them are going to be predominantly pH-dependent charge, and some of them are going to be a mix. Okay? So what we have here is we have a humic material and a smectite, a phyllosilicate and an organic molecule. Okay? And we're looking at the bottom here is we're looking at pH changes from 4 to 8. So the pH is increasing this way. Okay? And this is a measurement of its cation exchange capacity, i.e. how much cations it can hold on to it. Okay? Now, no anion measurement here. This is just cation. Okay? As the pH increases, I'm increasing the hydroxy. I'm increasing the hydroxyl molecules in my soil solution. If that's the case, those hydroxyl molecules are going to bind and pull off that proton that's on the hydroxyl that's part of the structure. Okay? So as it goes up, I'm going to be pulling that off, which means I'm going to get more negative charge on my structures. Okay? Here's my protons being pulled off of my humic material, and look what happens to the CEC, the ability of the humic materials to hang on to positively charged ions. It's getting more and more negative, so as a result, its ability to hold on to the cations increases. Does that make sense? As I go this way with the humic material, my capacity increases because my humic material is getting more and more negative. Right? Now let's look at the smectite on the other hand. Smectite, 2-to-1 mineral. Basically flat line until I get fairly high pHs where I'll get a slight pH boost on my ability to hang on to cations. But it's nothing like that. And the reality is here, smectites do have those hydroxyls exposed, but they don't have the abundance that are exposed in the organic molecule. Does that make sense? Questions? Go.
What's the ratio for smectite?
The ratio for smec...
For in terms of the...
it's 2-to-1. I don't know off the top of my head, but we can go back to smectite. Marillonite. It's basically right here. So the ratio is a charge formula right down here. Is that what you were asking?
I was just asking the 2-to-1.
Oh, I'm sorry. Yeah, it's a 2-to-1.
This has been a production of Cornell University, on the web at cornell.edu.